Distribution of SINR in millimeter wave D2D networks. Abstract. In this paper, the meta distribution of the signal to interference plus noise ratio SINR is a millimeter wave device to device network is studied, which is the distribution of the conditional SINR distribution given a realization of the point process modeling the network. This analysis provides much more fine-grained information on the performance of individual links than just a means that is usually evaluated. Modeling the D2D transmission as a poison point process (PPP) and considering the unique millimeter wave features moment of the conditional SINR distribution given the point process are derived in order to calculate analytical expression for the meta distribution. It turns out that when the size of the antenna array tends to infinity, the noise is totally suppressed and the noise density becomes the dominating factor affecting the interference in the network. Closed form approximation of the meta distribution with beta distribution are also provided. Numerical results give interesting insight into the effect of millimeter wave features on the performance of D2D communication. Introduction. Recently enabling D2D device-to-device D2D communications in millimeter wave networks has been regarded as a promising way for the next generation mobile networks to provide very high data rate, multi-gigabytes per second, for mobile devices with reduced end-to-end latency. First, for example, communication systems, the main challenge of implementing underlaid D2D links is difficulty in interference measurement between the inter-D2D interference and the cross-tier interference from other systems using the same spectrum, especially for the autonomous case without base station (BS) involvement. However, since the millimeter wave spectrum has several unique features such as spectrum availability, high propagation losses, directivity, and sensitivity to blockage, the situation will be different when the D2D communication occurs in the millimeter wave band. Thus, it is important to study how to exploit the interesting properties of millimeter wave communication for D2D networks and to analyze their performance. This is the motivation of our work. The signal to interference plus noise ratio SINR is fundamental metric for how a communication system links performs. When stochastic geometry is used for the analysis, SINR performance is most commonly characterized as the success probability relative to SINR threshold and evaluated at the typical link. However, the performance of the typical link represents an average over all the spatial realization of the point process or over all the links in a single realization if the point process is algorithmic, which provides very limited information on the individual links. To overcome this limitation, 3. Introduce the concept of the meta distribution, which is the distribution of the conditional success probability given the point process, and thus provided a much sharper version of the SINR performance. Although the benefit of combining millimeter wave and D2D technologies have attracted considerable attention recently, the existing works were investigated either through pure simulations or theoretical analysis with finite spatial extent 4 to 6. Only 7 analyzed the downlink coverage probability of a D2D relay assisted millimeter wave cellular network using stochastic geometry. To our best knowledge, there is no prior work that studied the meta distribution to provide fine-grained analysis for millimeter wave D2D networks. In this regard, we focus on meta distribution of the SINR in millimeter wave D2D networks, considering the unique channel characteristics and antenna features of millimeter wave communications. Expecting to get different insights from the previous D2D networks, we first derived the moment of the condition success probability for millimeter wave D2D networks, considering the effect of blockage, and the large beamforming gain from dictionary antenna arrays. It turns out that as the antenna array size tends to infinity, the noise is totally suppressed in this region. The node density as well as the side lobe interference become the dominant factor, affecting interference characteristic and hence the performance. Then to show what fraction of users in the networks achieve a target reliability if the SINR requirement is given, we provide analytical expressions for the exact meta distribution of the SINR. Closed form approximation of the data meta distribution with the beta distribution are also provided. The numerical results demonstrate the significant impact of the unique millimeter wave features, the SINR threshold, and the density of users on the performance of millimeter wave D2D networks. From broader perspective, the contribution of the paper lies in providing fine-grained information on the SINR performance for individual links rather than for the commonly studied typical link, which gives network operators a comprehensive understanding of performance differences among the individual users in D2D network model. We consider a millimeter wave D2D communications network where the D2D transmitters are distributed according to a homogeneous Poisson point process PPP with density. Each transmitter is assumed to have a dedicated receiver at distance R0 in a random orientation. For example, the D2D users form a Poisson bipolar network. We consider a receiver at the origin that attempts to receive from an additional transmitter located at R00 due to Slinyak's theorem. This receiver becomes the typical receiver under expectation over the PPP. We assume that each receiver has a single antenna and each corresponding transmitter is equipped with a square antenna array composed of an element. All transmitters operate at a constant power micro and apply analog beamforming to overcome the severe phase loss in the millimeter wave band. We also assume that the direction of the arrival DOA between the transmitter receiver pair is known at the transmitter, and thus the beam direction is perfectly aligned to obtain the maximum power gain. The ROA channel access scheme is adopted, i.e., for example, in each time slot D2D transmitter in pi independently transmit with probability p, blockage and propagation model. The generalized loss Bohr model 8 is used to capture the blockage effect in millimeter wave communication since it has been validated in 9 as better fit with real-world scenarios than other blockage models adopted in previous work. Specifically, the LOS probability of the channel between two nodes with separation d in the model is PROSD, PLLDR, where 1 is the indicator function, R is the maximum length of LOS channel, and the LOS fraction constant PL represent average fraction of the LOS area within a circular bore of radius R around the receiver under consideration. Thus, PL is the LOS probability if the distance d is less than R. The blockage effect induces a different phase loss exponent, denoted as alpha L and alpha N, for loss and n-loss channels, respectively. Typical value for millimeter wave path loss exponent can be found in measurement result in 10 with approximate range of alpha L 1925 and alpha N 2547. For the sake of mathematical tractability, the sectorized antenna model is adapted to approximate the actual antenna pattern as in 8. In particular, the array gains within the half power beamwidth are assumed to be maximum power gain, for example, main lobe gain, and the gain of the other DOAs are approximated to be the first minor maximum gain, for example, side lobe gain. of the actual antenna pattern, which can be formulated as like this, where W is the half power beam with and correlated with the size of antenna array, and rho in is the angle of the bore sight direction, with the assumption of n root n times n uniform planar square antenna array with half wavelengths. Table 1, antenna parameters of uniform planar square antenna array 7. Antenna spacing, the half power beamforming W, main lobe gain Gm, and the side lobe gain G8 are summarized in Table 1. SINR analysis, we assume that link between the transmitter-receiver pair is in the loss condition with deterministic path loss R0 minus alpha L. In fact, if the receiver was associated with N-loss transmitter, the link would quite likely be in outage due to the severe propagation. If the receiver was associated with the N-loss transmitter, the link would quite likely be in outage due to the severe propagation loss and high noise power at millimeter wave band, as well as the fact that the interferer can be arbitrarily close to the receiver. The power fading coefficient associated with node X is denoted by the Hx, which is an exponential random variable with EHx Rayleigh fading. For both the ROS and NOS to enhance the analytical tractability, and all Hx are mutually independent and also independent of the point process. Rx is the random path loss function associated with the interference transmitter location X, given by like this, where all Lx are independent for the typical receiver. The interference outside the loss bore are NO loss and thus can be ignored due to the severe path loss over the large distance N-list R. As a result, the analysis for the network originally composed by the PPP with the density lambda reduced to the analysis of finite network region, namely the disk of radius are centered at the origin. Due to the incorporation of the blockage, the loss transmitters with loss propagation to the typical receiver from the PPP with density P and lambda, while with density P and lambda is the transmitter sandwich NOS propagation, where PL plus PN equal 1, such as pi L pi n. Thus interference at the origin defined as I equals sigma where mu is a constant transmit power, G is a directional antenna gain function with DOA, and Bx is a Bernoulli variable with parameter P to indicate whether X transmits a message to each receiver. Since all transmitters are oriented toward the corresponding receivers, the DOAs between the interference and the typical receiver are uniformly random in pi. Hence, G log X is equal to Gm with probability W a pi W and Gs with probability 1 minus W. Without although loss-dependent millimeter wave scenarios may be more in line with Nakamoto fading, simulation results have shown that Nakagami and Rayleigh fading present the same trend in terms of SINR performance. Loss of generosity, the noise power is set to 1, and the SINR at the typical receiver is then given by SINR equal like this. The meta distribution of the SINR. In this section, we focus on the meta distribution of the SINR, which is the distribution of conditional success probability given a realization of the point process. The meta distribution of the SINR is a two-parameter distribution function defined as this, where theta r plus it represents the complementary cumulate distributed function CCDF of the link success probability PS conditioned on the point process. Here P denoted the reduced palm probability conditioning on the typical receiver at the origin row, and each corresponding transmitter to be active, and the link success probability PS theta is a random variable given as where theta is SINR threshold due to the ergodicity of the point process. The meta distribution can be interpreted as a fraction of the links in each realization of the point process that have SINR greater than theta with probability n-least x. Hence, the standard success probability in the mean of PS theta obtained by integrating the meta distribution 6 over x 0, 1. A moment of PS, since the direct calculation of the meta distribution seems infeasible, we will derive the exact analytical expression through the moment MB theta EPS theta first, and then approximate it with much simpler closed form expressions. Theorem 1, moment for millimeter wave D2D network with ROA. Given that the typical links is LOS and active, the moment MB, BC of the conditional success probability in millimeter wave D2D networks is like this. The first moment of the conditional success probability in the standard success probability for the millimeter wave D2D networks, denoted as PS theta or M1 theta, it is given as the variance of the conditional success probability can be obtained as bar PS theta equal M2 theta minus M12 theta, as is seen in 3. We also find the millimeter wave D2D networks that the same lambda p leads to the same standard success probability, but the variance depends on both lambda and p, not just the product, which highlight the importance of the fine-grained analysis based on the meta distribution. Moreover, in millimeter wave D2D networks, as in bipolar networks with standard path loss and the signal antenna nodes, we also have the following concentration property. Corollary concentration as P, keeping the transmitter density T fixed and letting P 0. We have in mean square and probability and distribution. Proof from the expression of in 13, when P0 we have and thus M2 theta equal M12 theta. In this case, the limiting variance is 0. For example, limit P0 lambda Pt bar PS theta equal 0. The concentration property means that in the limited of very dense network with very small p, all links in the networks have exactly the same success probability or reliability. An interesting question is what happened when massive antenna arrays are used in millimeter D2D nexus, for example, as n to it is answered the following corollary. Where step A uses the general binomial theorem and follows from the definition of Gaussian hypergeometric function in 12 chapter 9.11. The limited 16 offers the following insight. As n, the effect of the noise is totally suppressed since Gm. The side lobe interference gradually becomes the main performance limiting factor as n. In this region, the node density plays a critical role in determining the interference power in the network. For instance, a sparse network makes the interference in the massive MIMO, massive input, massive out network arbitrarily small, while a dense one is interference limited. Exact expression. The exact meta distribution can be obtained by the Gilpin-Rice theorem with the imaginary moment MJT of like this. Corollary exact expression. The meta distribution for the millimeter wave D2D networks is given by denoted the real and imagined part of ZC respectively. Proof. According to the Gilpin-Rice theorem, the CCDF of the P theta is given by like this, where MJT, MV, JT, TR is given 8, and is the imaginary part of ZC, letting we have like this. Approximation of the meta distribution. Though the expression in core 3 is exact and can be calculated via numerical integration techniques, it is difficult to gain insight directly and apply it to obtain analytical result. To approximate the meta distribution, we use the same approach adopted in 3 by matching the mean and variance of the beta distribution with M1 theta and M2 theta given the theorem 1 to verify whether the approximation is also acceptable for millimeter wave D2D networks, where the interference characteristics are different from those microwave networks. The probability density function, PDF, the probability density function, PDF of beta distribution random variable x with parameters k and beta is fx equal xk1 1 minus x beta minus 1 per bk beta. Whether b is a beta function, the first and second moment of x are given as hence the approximate meta distribution of the typical millimeter wave D2D receiver follows as like this, where kb is a regularized incomplete beta function numerical result. In this section, we give some numerical result of the standard success probability and the meta distribution for millimeter wave D2D networks, where lambda equals 0.1, micro 20, theta 0, r03, p 0.5, pl 0.2, alpha 1 2.5, alpha n 4, r equal 200, and n equal 4 are default values. Figure 1, the standard success probability M1, the variance M2 minus M1 squared of the conditional success probability. Meta distribution for different lambda and p with n equal 4, pl 0.2. Meta distribution theta equal minus 10, minus 5, 0, 5, 10, 50 decimal. The impact of millimeter wave features, directional transmission and sensitivity to blockage are two key features of millimeter wave communication. In this subsection, we focused on the impact of loss probability, low PL and antenna array size, and on the mean and variance of conditional success probability, PS theta. As shown in figure 1, increase the number of antennas improve the standard success probability due to the fact that larger antenna array can form narrower beam, thus causing less interference. As the number of antennas tend to infinity, the standard success probability converge to an upper limit C-core 2. Since the side lobe leakage restriction, the performance improvement. However, for the loss probability, a higher PM means the number of loss links is larger, leading to more severe interference. Thus, the standard success probability deteriorate with the increase of PL. Figure 2 presents the values of the conditional success probability as a function of theta for different PL and then S n. Since the variety necessary tend to 0 for both theta to 0 and theta to, it assumes a maximum at the finite value of theta. It can be seen that given a PL, the theta with the maximum variance increase with n and converge to an upper limit, similar to M1. Moreover, a large PL lead to smaller variance because in loss environment with smaller path loss exponent, the randomness of the spatial relative locations between the interference and the receiver has a smaller effect on the variance of the interference than the LOS and LOS cases. Meta distribution B. Meta distribution in millimeter wave band. Figure 3 compares the exact result and the beta approximation for lambda p equal 0.05 with different lambda and p respectively. As seen from plots for the given system parameters, the approximation match the exact result extremely well. Moreover, the three curves have the same value of lambda p and hence the same standard success probability, but the corresponding meta distribution are rather different. This shows that the standard success probability provides only limited information on the network's performance. Figure 4 shows the meta distribution for different SINR thresholds, which enables a precise statement about what fraction of links achieve an SINR threshold with a target reliability. For example, theta minus 5 decibel, about 90% of the links have successful probability at least 80%, while for theta 5 decibel less than 10% of the links achieve the same reliability. Conclusion. In this paper, we analyzed the meta distribution of the SINR for millimeter wave D2D networks and provide an exact expression as well as approximation with the beta distribution, which turns out matching the exact distribution extremely well. Hence, the complete distribution of the conditional link success probability in Poisson bipolar networks can be characterized, which provide more fine-grained information about the performance of the individual links than just the mean. For example, the standard SINR distribution at the typical link. Moreover, the millimeter wave D2D networks with directional antenna arrays exhibit the key insight that when extremely massive antenna arrays are used, for example, the noise is totally suppressed and the interference behavior depends on the density of concurrently achieved link. Numerical results show the significant impact of the unique millimeter wave features on the performance and the advantages of meta distribution, helping the network operator acquire comprehensive knowledge to the performance of individual links of users.